We're on Unit 11, and Unit 11 deals with convergence and divergence of series. In this first section, we are going to define convergent and divergent infinite series, and we're going to get our first test to determine if a series converges or diverges, and that is the nth term test for divergence. So let's begin by reminding ourselves about factorials. We're going to have a lot of factorials in this unit and in our next unit as well. So let's remind ourselves how a factorial works. If we have 5 factorial, that means we're multiplying 5 times 4 times 3 times 2 times 1. So it's a product of 5 times the next integer lower times the next integer lower all the way down to 1. And if we were to multiply all that out, you would find that that is 120. We're going to get to where we recognize several of these factorials. 1 factorial is just 1. 2 factorial is 2 times 1, so that will just be a 2. 3 factorial is 3 times 2 times 1, so 6. 4 factorial, if I multiply 3 factorial times 4, we get 4 factorial, which is 24. If I multiply 4 factorial times 5, I'll get the 120 that we see here. 6 factorial is 720. So it'll be nice if you recognize the factorials up to and including 6 factorial. Okay? So in general, n factorial would be n times n minus 1 times n minus 2 times n minus 3, and I could keep on writing as long as I like. Once I've established the pattern, I can just say times dot 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 all the way down to 1. And that would be how we would write n factorial if we were expanding it. So in C, we have n factorial divided by n plus 2 factorial. We're going to simplify this. So when I simplify it, I think to myself, okay, I'm going to go to the larger value. N plus 2 is larger than n, so I'm going to go to this n plus 2 factorial, and I'm going to write out several terms of that. So n plus 2 times the next lowest term will be n plus 1. The next lowest term would be n, or lower term would be n. And then I would keep on going, n minus 1, n minus 2, n minus 3, all the way down to 1. Up on top here, I have n factorial, which is n, times n minus 1 times n minus 2, all the way down to 1. And we see that we can reduce the n's, the n minus 2, this n minus 1s. n minus 2 would reduce with the n minus 2 that's down here, all the way down to 1 would all reduce. And I'd be left with 1 in the numerator, and then n plus 2 times n plus 1 in the denominator. Okay? So, if you think about that, right here, this is n factorial, and right here, this is n factorial. So the n factorials reduce out, leaving the n plus 2 and the n plus 1 in the denominator. So again, 1 factorial is just 1. 0 factorial is by definition 1. And some students don't like that when I say by definition. So let me give you a brief little proof of why that has to be true. N factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. So that is n times n minus 1 factorial. Okay? So if I replace n with 1, I'll have 1 factorial is 1 times 0 factorial. Right? Because 1 minus 1 here would be 0. And so 1 factorial is 1. This is 0 factorial. So 1 must be 0 factorial. It's my little attempt at a proof of that. Okay. So let's give a couple of definitions here. A sequence is simply a list of numbers in some pattern. we can call those a sub 1, a sub 2, a sub 3, dot, 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 a sub n, dot, dot, dot. So a sub n is called the nth term, and that is a way that we can write a general pattern, a general sequence. A series is the sum of the terms of a sequence. So if we take all the terms in the sequence and add them up, we'll get a series. For this unit, we will just say series to mean an infinite series. So when I say series to you, it means an infinite series, unless I say finite series. If I say finite series, then it's finite, not infinite. The initial n value here, this initial n value happens to be a 1. Usually it is a 0 or a 1, but it can be any positive integer. N serves as a counter, and that's all it is. It just counts where you are in the series or sequence. If you see a series written like this, without any n equals something to something, this is assumed to go to infinity. You can assume that it goes to infinity. The initial n value here can many times be taken from the context of the problem. So if you start with this in a problem, and then you can just write sigma, and it's implied to remain the n equals 1 to infinity, unless you change it. All right, the nth partial sum of a series, so the nth partial sum of an infinite series is the sum of the first n terms of the series, and it's denoted by s sub n. So we have an infinite series. If we want to stop it, if we want to make it finite, we can call it s sub n, and that would be the sum from 1 to whatever n is, whatever your number is here. I shouldn't call it n, but that would be whatever, the sum of the first n terms. Okay. The entire infinite sum of the series is denoted by s, no subscript. If there's no subscript on the s, that means it's infinite. All right. So as n goes from 1 to infinity, a sub n would be just s. Okay. We say that an infinite series converges if the limit of its sequence of partial sums exists and is equal to s. We say that the series diverges if the limit of its sequence of partial sums does not exist. I know that sounds weird. We're going to look at some examples here. Okay. This might be because the limit goes to infinity, negative infinity, or it oscillates between two numbers. So we're going to be dealing with limits of sequences of partial sums. So the limits of the sequence of partial sums. So in other words, we'll look at some examples. So written in math, if the limit as n goes to infinity of s sub n exists, then the series converges and the sum is that limit. This is important. If the limit as n goes to infinity of s sub n does not exist, then the series diverges. So again, that might be because this limit is infinity, negative infinity, or it oscillates between numbers, or it just doesn't come to a single number. Remember that a limit existing that's important, right? It means that it exists and it is equal to a number. All right. Let's take a look at some examples. So in example 1 here, you see the sum in sigma notation, and then you also see that I wrote out many terms here. Okay, we're going to write the first 10 terms in the sequence of partial sums. So s sub 1 would be the sum of one term. So it is just your first term. S sub 1 is the first term. So that is at 1.5. Okay? In the sequence, because this is a sequence, so I'm going to separate it by commas. In the sequence, the next term is the sum of the first two terms. So if I add 1.5 plus 0.75, I'm going to get 2.25. Okay? S sub 3 will be the sum of the first three terms. So if I take that 2.25 and add 3/8, I'm going to get 2.625. So that's S sub 3. S sub 4, I add 3/16 to S sub 3, and that gives me 2.8125. Now I'm going to add the next term in the sequence. So I'm adding 3 over 32, and I get 2.90625 in my calculator. Add the next term, and I get 2.95313. Add the next term, 2.97656. Add the next term, 2.98828. Add the next term, and I get 2.99419. And then add this last term, which look how small it is. The next term, and I'm going to get 2.99707. Okay? This sequence would continue. Would it ever end? No, because I can keep writing more and more terms here and keep adding. I will be adding a tinier and tinier number each time, though. So I ask you, and in class I would ask this, what is your conjecture for the limit as n goes to infinity of S sub n? So what do you think this sequence is going to? I'm searching for my power cord here. Okay, so it appears that this sequence is approaching 3. So my conjecture is that this limit is 3. Does this series appear to converge or diverge? Well, if I think that the limit is 3, then this series appears to converge. And it appears to converge to 3. Okay? That's the meaning of convergence of a series. Let's take a look at number 2. Write the first 10 terms in the sequence of partial sums for this one. Well, S sub 1 is just the first term. S sub 2 would be the sum of the first two terms. S sub 3, I would add the 7 to the 8, so 15. S sub 4 would be 24, and then we would have 35, and then 48, and then 63, and then 80, and this would keep on going. Keep on going. What is your conjecture for this limit for the limit of this one? Well, this one does not appear to be stopping. It appears to be growing larger with every term. So this, I'm going to say, is going to infinity. It appears to be going to infinity. So does this series appear to converge or diverge? This one appears to diverge. Okay? So that's the meaning of a divergent series. In this unit, we will be concerned with two questions. Does the series converge or diverge? If the series converges, can we find out what its sum is? We are going to learn 10 tests to determine whether a series converges or diverges. And in most cases, if the series converges, we will not be able to actually find its sum. We will only be able to determine that it converges. We don't know what it converges to. In this unit, we can find the sum only in two types of series. Okay? All right. Now, we're going to get our first of the 10 tests. and that is called the Nth Term Test for Divergence. This test can only be used to determine if a series diverges. You can never say that a series converges by Nth Term Test, only for divergence. Okay? And this is a very simple test. Take the limit of the nth term as n goes to infinity. If you do not get 0, then the series diverges. Okay? If you do not get 0 for that limit, the series diverges. Now, that does not mean that if you do get 0, the series converges. That's not true. If the limit is 0, then you go and use one of our other 9 tests that we're going to learn. Okay? Kids really like to say, oh, the limit is 0, it converges. But that's not enough. It's not true. This test can only be used to prove divergence. If the limit is 0, we know nothing. Not a zilch, nothing at all. Okay? All right. This is a common sense test, I think. If the nth term, as n goes to infinity, if the nth term is not 0, then clearly you're always adding numbers other than 0. So the sum cannot converge because you keep on adding something every time that's significant. Okay? However, if the nth term is 0, maybe it converges, maybe it diverges. We don't know. If the limit is 0, again, we go and use one of our other 9 tests. I keep repeating that because that is a common mistake I see. Kids take this limit, they find out it's 0, and they say that it converges by nth term test. Can't do it. Just not true. All right, examples. We're going to determine whether these series converge or diverge. So, the only test we have so far is the nth term test. So that's what we're going to be using on every one of these problems. So I'm going to take the limit as n goes to infinity of a sub n. Here's a sub n right there. So 2n plus 3 over 3n minus 5. Here's the way I want you to think of it. Here's the way I need you to think of it. As n goes to infinity, please do not use the top no, bottom o, same co rhyme, because you're not always going to have polynomials, all right? You're going to have other things going on, and I need you to know why that rhyme works, because then you can use it, the why, you can use the theory on all of the problems. So, as n goes to infinity, the 3 and the 5 are insignificant as n goes to infinity. I'm left with 2n over 3n, the n's reduce, and I get 2/3. That's your thought process. It's quick, it's easy, it's easier than that rhyme. So please use this. All right, 2/3 is not 0. The limit is not 0. Therefore, the series diverges by the nth term test for divergence. That's what you'll write. Okay? All right. Number 2. We're going to take the limit as n goes to infinity of n factorial over 2n factorial plus 1. Okay, our thought process as n goes to infinity, the plus 1 is insignificant. I'm left with n factorial over 2 times n factorial. And by the way, 2n factorial means 2 times n factorial. It does not mean 2n factorial. Okay? For some reason, some students want to do that, and it's not true. Okay? So, 2n factorial is 2 times n factorial. I tell kids, if you have 2x squared, or let's make it 3x squared, does that mean the 3 is being squared also? Does that mean we have 3 squared x squared? And kids say, no, of course not. But for some reason, they want to apply the factorial to both of these. Okay? Don't do it. All right. The n factorials cancel, and we get 1 over 2, which is not 0. Therefore, the series diverges by the nth term test for divergence. Number 3. Limit, as n goes to infinity, of 3 to the n minus 2 over 3 to the n. As n goes to infinity, the minus 2 is insignificant. I'm left with 3 to the n over 3 to the n, which reduces to 1. 1 is not 0. So therefore, the series diverges by nth term test for divergence. Okay, number 4. For number 4, I have this, so I have the limit as n goes to infinity of a sub n, which is this guy. Okay, all right. Well, as n goes to infinity, I'm going to have a large unbounded number here, and then I have 1 over a large unbounded 0, so this is going to 0. So 1 plus something going to 0 is something going to 1. So right here, this is going to 1. That's going to 1 over something going to infinity, right? Well, something going to 1 raised to a power of something going to infinity, this is indeterminate. This is something that we did back when we did L'Hopital's rule. Okay? I think I'm going to take a moment and go through it again with you to show you how we would handle this. This is how we handled this when we were doing L'Hopital's rule. We said, okay, this is indeterminate, so I need to mess with it. I need to somehow get to a point where I can apply L'Hopital's rule. 1 to the infinity is not a L'Hopital's form. We have to get it to be 0 over 0 or infinity over infinity. So here's how we did it. We said, I'm going to let y be that limit, and then I'm going to take the natural log of both sides. Do you remember doing that? Natural log of both sides. And then I'll have natural log of y is equal to the natural log of a limit is the limit of the natural log and now I can use my log properties. So this exponent I can pull in front of the log. Okay. And now I'm going to write this n. I need, for L'Hopital's, remember, we need to get it to be a fraction. So I'm going to write this as ln of 1 plus 1 over n divided by 1 over n. If I move that into the bottom, it's going to be a 1 over n. Now if I let n go to infinity, I have inside here, I still have something going to 1. Natural log of something going to 1 is 0. That's 0. So this is going to 0. And if I put infinity in here, this is also going to 0. So now I can use L'Hopital's rule. And if I use L'Hopital's rule over there, I'm using L'Hopital's, this will be the limit of, so I need the derivative of the top will be the derivative of the argument divided by the argument, right? So the derivative of the argument will be 0 minus 1 over n squared. That negative 1 over n squared is the derivative of 1 over n, divided by the argument, yeah, all divided by the derivative of the bottom, which is that negative 1 over n squared. The negative 1 over n squareds will cancel out, and I'll be left with just 1 over 1 plus 1 over n. And now if we let n go to infinity, this piece is going to 0. I'm left with 1. So ln of y is equal to 1. Therefore, what is y? Well, y will be e to the first, or just e. So this limit is equal to e. Okay? That is the definition of, that's the definition of e. Okay? From now on, you don't want to have to go through this every time you get this. So memorize it. I need you to memorize the definition of E now. Okay. Moreover, I need you to memorize the general form of the definition of E. Look it over here in number 5. Okay. Very similar. They're very similar, except in place of the 1, there's a 5, right? This, when we write it as a limit, the limit of a sub n here will be e to the 5th. I need you to recognize that form. Okay? So, this limit is e, which is not 0, so I know that the series diverges by nth term test for divergence. Okay. All right, number 5. Well, I know this limit is equal to e to the 5th, which is not 0. Therefore, the series diverges by nth term test for divergence. Okay. Number 6. So we have the limit as n goes to infinity of 3n factorial plus 2 divided by 9 to the n plus 7. Well, as n goes to infinity, the plus 2 and the plus 7 don't matter, right? Then I'm left with 3 times n factorial divided by 9 to the n. And my question is, what in the world do we do with that? Nothing reduces, right? When things like this don't reduce, and you're examining this, you want to know what is happening here. As n goes to infinity, where does the power lie? I want you to consider, and I want you to know some of the powers of infinity. I want you to know which ones have strength, which ones are weak. They're all going to infinity here, but which ones are more powerful than others? So at the top of the list, very top of the list here for us is n to the n. N to the n, I'm going to call Big Daddy. And if Big Daddy is around, he's going to control. He's the power. He's infinity. If Big Daddy's not there, then you look for Big Mama. And here's Big Mama, n factorial. So this is Big Mama. Okay? Next up in line, if neither of these are around, then you're going to look for a number to the n power. A number to the n power, where n is a constant. I don't have a name for that one. It's just a to the n. Okay? Next up, you're going to look for like a polynomial type of thing. So n cubed, n to the 4th, n to the 5th, n squared, n to the 1st, n to the a power, where a is any constant. Okay. Last up in the line up is natural log of n. Natural log of n does go to infinity, but is weak. It's so weak. Think of the graph of natural log. Natural log does this. Is it going to infinity? Yeah, eventually. If I remember, I did this a long time ago, but natural log of a very, very, very large number, 23. Yes, it goes to infinity, but you've got to have an extraordinarily large argument to make this a large value. So it's very weak. Here are your powers of infinity I need you to know. It'll make these types of problems very easy. As n goes to infinity, I see Big Mama. I don't see Big Daddy, but I see Big Mama, and Big Mama's going to rule, so that's where the infinity. So this acts like infinity over 1, which is infinity. Okay? Infinity is not 0. Therefore, the series diverges by nth term test for divergence. And probably long before now in class, somebody would say, Miss Murray, do we have to write that every time? Okay. I'm going to let you abbreviate, okay? But I'm going to keep on writing it the long way, just to drive home the fact of what this is doing. Okay. Number 7. We're going to take the limit as n goes to infinity, 2 to the n minus 17 over n squared plus 4n plus 10. Okay, you're going to ignore, as n goes to infinity, the negative 17 is insignificant, the plus 10 is insignificant, and the plus 4n is insignificant compared to n squared. You're going to ignore everything except the largest power on top and the largest power on the bottom. That's what you're going to be looking at. So I have 2 to the n divided by n squared. That's what this behaves like. Which is more powerful? Well, 2 to the n is more powerful than n squared. So this behaves like infinity over 1, which is infinity, not 0. Therefore, the series diverges by nth term test for divergence. Okay, number 8. Limit n goes to infinity, n cubed minus 6n minus 100 over natural log n plus 10. Okay, as n goes to infinity, the minus 100 is insignificant, the minus 6n is insignificant, this plus 10 inside here is insignificant. As n goes to infinity, this behaves like n cubed over ln of n, which goes to infinity since n cubed is more powerful than ln of n. Infinity is not 0, therefore the series diverges by the nth term test for divergence. Okay, that is our introduction to sequences and series, and the first of our 10 tests, the nth term test for divergence.